Case Western Reserve University's Great Thinker Series proudly presents the Origin Science Scholars Program. These lectures are presented by the Institute for the Science of Origins, a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream, with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. My name is Glenn Starkman. I'm the director of the Institute for the Science of Origins, as well as professor of physics at Case Western Reserve University, and your host for this series, and tonight your speaker. So let's dive right into it. Tonight I'd like to talk to you about the Standard Model, and in particular, is the Standard Model enough, or do we need more? So I'll start by talking about the Standard Model a little bit. What is it? And then ask, if the Standard Model isn't enough, what else might there be? So I'll talk a little bit about grand unification and about supersymmetry. And I would have loved to talk to you also about extra dimensions, but that's worth a whole lecture, so we will save that for another time. All right, what is the Standard Model? Well, it's the Standard Model to explain the behavior of what scientists, what physicists call matter. What's matter? Well, it's pretty much everything around you, from the Eiffel Tower to Niagara Falls to vegetables to the people around you. It's basically everything that you can touch and everything you can see. And it's all made of atoms. Well, saying it's made of atoms, atoms are not fundamental particles. Atoms themselves are made of things, and that's what this picture shows, right? It shows that an atom is made of these things at the center that are big and heavy, called nuclei, and these things that go around them, called electrons. Okay? So electrons are charged particles, negatively charged particles. We call them leptons. The word leptons means light particles. That's all it means. To contrast them with the other particles that are inside the nucleus, the proton and the neutron, that we call hadrons, which means heavy particles. But protons and neutrons, the electron is a fundamental particle as far as we know. It doesn't seem to have any substructure. You try to break it apart and there's nothing to break. That's not true of the proton and neutrons. For about 50 years, we've known that protons and neutrons are made of other things. They're made of things that we call quarks. So a proton is made of two up-type quarks, here with the letter U, and a down-type quark. And a neutron is two down-type quarks and an up-type quark. So the fundamental particles are not the proton and neutron, but the quarks. And everything around us is made of just those three things: electrons, up quarks, and down quarks. But there are other particles out there. We've known for a long time about a particle called the neutrino. In fact, it was a fellow who was later the chairman of the Department of Physics at Case Institute of Technology, this fellow Frederick Reines, who got the Nobel Prize in 1995 for the detection of neutrinos together with Clyde Cowan, something they did in 1956. Actually, and he came back here 3 years later from 1959 to 1966 to chair the Department of Physics. And it would be nice and simple if that's all there was. He found those electron neutrinos coming out of nuclear reactors in nuclear reactions. But we've discovered lots of other particles. It turns out that there aren't just those four. There's actually a set of particles called the muon and the tau that are exactly like the electron except heavier. And there's a particle called the charm quark, which is just like the up quark except heavier. And another one called the top quark, which is just like the charm and the up quark, but heavier still. And similarly for the down quark and the strange quark and the bottom quark. And there's not one type of neutrino, but in fact three types of neutrino, one associated with each of the charged leptons, so a electron neutrino, a mu neutrino, and a tau neutrino. And those are the particles of what we call matter. Now, as I said, all of the ones that we actually see around us in real life, everyday life, are made of electrons and up and down quarks. These other ones are made in accelerators. We find them in cosmic rays, so in high energy environments, but not in stable, ordinary matter. Okay. And then there's also all of their antiparticles. So we're not going to talk much about antimatter. In fact, we're not going to talk at all about antimatter. But each one of these has a partner, which is its antiparticle. So that's one part of the Standard Model, the particles that make up matter. The other part of the Standard Model is the forces that these particles interact with. So the Standard Model describes how all these particles interact with each other. And the one we're most familiar with probably is electromagnetism. And that's the force that keeps electrons going around nuclei, because electrons are negatively charged and the protons inside the nucleus are positively charged and they attract each other, and that binds together atoms. That keeps atoms bound together. In fact, it keeps sets of atoms bound together. So electromagnetism is what is responsible for molecules like water or DNA. And it's what's responsible for materials like water or oil or steel or rocks or any of the things we see around us. Those are all bound together by electromagnetism. So that's a very important force. But it's not what binds together the quarks inside of a proton or neutron. It can't, because for example, the up quarks both have the same charge, and so they should be pushed apart from each other. The down quarks both have the same charge, and so they should be pushed apart from each other. Electromagnetism cannot keep quarks bound inside of nuclei. For that, we require a different force that we can call the color force. And sometime we might have a detailed discussion of it. In fact, maybe next week with Professor Lin. He might tell us all about the color force. It's also related to something called the strong nuclear force, which is what binds together protons and neutrons into nuclei. Okay? So we have electromagnetism that binds everything above the level of nuclei. So nuclei, electrons are bound to nuclei, into atoms, atoms are bound to each other, into molecules, molecules are bound to each other, into more complex materials. That's all electromagnetism, but what's holding together those protons and neutrons is the color force. And the strong nuclear force binds those protons and neutrons into nuclei. Okay. Well, there's another force called the weak nuclear force, unlike the strong nuclear force. And when people ask, well, what does that do? How can I see that force? We give this very strange answer, which is it doesn't really, it's not a force in the conventional sense of pushing and pulling on things, or at least it does that so weakly, hence the name. But it is, we should really call it the weak nuclear interaction. It's a way that particles interact with each other, and it's responsible for all sorts of nuclear decays. So nuclei will emit electrons, and in that process, a neutron inside the nucleus is turning into a proton. And they're also sending out neutrinos or antineutrinos. So three important forces that are described by the Standard Model. Now, you might have noticed that I missed one force that we all know of, which is gravity. Okay. So the gravitational force, which is we've understood for a lot longer than any of the other forces, is kind of only peripherally part of the Standard Model. When we talk about the Standard Model of particle physics, we don't know how to combine gravity with it on the same footing. And people will talk about a theory of everything, or string theory, which is an example of an attempt to come up with a theory of everything. That's how to include gravity with the other three. But we're going to leave gravity off because that's not principally part of the Standard Model. Now, each of those forces comes with a particle that carries it. So right now you're seeing me because particles of light, called photons, are bouncing from the lights, hitting me and coming into your eyes. But those particles of light called photons, they're responsible for carrying this electromagnetic force. The color force is carried by a particle called a gluon. And instead of one type there's one type of photon carrying electromagnetism, but the color force has 8 different types of gluons. And we can think of them as red and anti-red and blue and anti-green and these kind of different colors. But what's important for us is that there are 8 of them. And finally, this weak nuclear force, which isn't really a force at all but an interaction, it's carried by 3 quite heavy particles, Unlike the photon and the gluon, which have no mass, the W plus, the W minus, and the Z, they weigh more, they have masses more than 100 times the mass of a proton. So quite heavy, is kind of the mass of a lead nucleus. And that's it. Those are the particles that carry forces in the Standard Model that determine how all of those quarks and leptons, those electrons, those up quarks, those down quarks, interact with one another. There's one more particle in the Standard Model, and it's been in the news a lot over the last few years because it was finally discovered after 50 years of looking for the particles of the Standard Model, and it's called the Higgs boson. Okay? And that's it. Those are all the particles of the Standard Model. So we have all the particles of the Standard Model, we have all the forces of the Standard Model, and they explain all of the interactions that we have ever measured between all of the particles that we have ever discovered. That's pretty incredible. So if that's true, why do we want to go beyond the Standard Model? Why do we want to invent physics that's not included in the Standard Model, which is such a successful theory? Well, the first thing is that from a theoretical physicist's point of view, the Standard Model has too many forces. Right? We said that there was a color force binding together the quarks. There was an electromagnetic force binding electrons into atoms. There was this weak nuclear force / interaction, which was responsible for decays. And we can count gravity or not count gravity as a fourth force. And that's too many forces, even if you only count 3 of them. What do I mean by too many forces? Well, we have this idea that 3 is a big number. It's hard to count that high. We'd much rather have 1 force, if only we could. It's also true that the Standard Model has too many particles. I mean, these are the ones I showed you, right? The photon, the W plus, the W minus and Z, the 8 gluons, the Higgs, electrons, muons, taus, the neutrinos, 6 types of quarks. That's a lot of particles. And I was actually simplifying things a bit because those particles come in left and right-handed varieties. Okay. And the quarks, they come each in 3 colors. So there really are a lot of particles in the Standard Model. And we'd really like if there was far fewer, maybe 1 or 2. Or at least if I could think of them somehow as all just different aspects of the same. And the Standard Model doesn't let me do them. It really says, okay, the photon is 1, and these 3, I can think of them as different aspects of the same particle. And okay, I'll count the gluons as 1, but I have to count all of these. These 2 I can count as 1 together, and these 2, but there's 3 of them, and oh my God, when I get to the quarks, it's such a mess. The Standard Model also has too many parameters. That means numbers that I have to go out and measure. It has a lot of them. The electron has a mass. I have to go measure that. I can't predict that. So does the muon, and so does the tau, and so does the up quark and the down quark, and the strange quark and the charm quark, and the bottom quark and the top quark. And there's these things called the mixing angles that describe the relationships between the down and the strange and the bottom quarks, and the special angle called delta that describes how things do or don't, the extent to which if you run a movie backwards, it doesn't look the same. And then there's 3 numbers called alpha 1, alpha 2, and alpha 3. Those are called coupling constants, which is a complicated word for saying how easily do photons couple, how easily do photons interact with electrons? There's a number that describes that. It's called alpha 1, well, sort of, alpha E. And there's a number that describes how well do gluons, these particles that carry the color force, interact with quarks. That's called alpha 3. And there's a number that describes how well do these W and Z particles interact with electrons or with up and down quarks, and that's called alpha 2. We're not done, because the Higgs has a mass, it can couple to itself, and the neutrinos have masses and can mix with each other, and there's a lot of numbers. Too many numbers. It would be great if there was just 1. Now, the other thing is about some of the numbers in the Standard Model is that they are very, very big. So if I take this number, this mass called the Planck mass, which describes how strong gravity is, And gravity is very, very weak. I know you don't think it's very weak because we feel it all the time, right? We sit down and we feel gravity. We get on the scale in the morning, we feel gravity. But gravity is actually very weak, and let me prove it to you. The entire Earth is pulling on this pen, and I can beat it. I can lift this pen with electromagnetism, despite the fact that the entire Earth is pulling on this pen. That's how weak gravity is. So gravity, the weakness of gravity, is tied up in the largeness of this mass called the Planck mass. And it's large compared to another characteristic mass in my theory called the Higgs mass. And their ratio is the number 10 to the 17. That's 100 million billion. That's a big number. There's other big numbers. For example, the mass of the top quark, the heaviest particle whose mass we know, and the mass of the electron, the lightest particle whose mass we've measured, of those quarks and leptons, is about 100,000. But then if you take the masses of neutrinos, which we now know have mass, the ratio of the top quark to the neutrino mass is like 10 to the 13, 1 with 13 zeros after it, or 10,000 billion. That's another really big number. We don't like big numbers. We like 1 or 0. Those are beautiful numbers. Okay. Now, you might have noticed that none of these are experimental failures of the standard model. They're what we might call aesthetic failures of the standard model. And that's because the standard model has no experimental failures. The standard model is not beautiful, but it has no experimental failures.
So where does dark matter fit in terms of, is it a new particle that they're conjecturing, or does it made up of the existing standard model?
Dark matter is something that we so far see only through gravity. Okay? So if it exists, and we're not sure it exists, but it's the simplest explanation, or it's a very simple explanation for what holds galaxies together and clusters of galaxies together, stops them from flying apart, it could be a particle. It is not a particle of the standard model. None of the particles up there is dark matter. So there's two possibilities. One is that it's a new particle. And some of the theories I'm going to mention in a moment lead to possible new particles that could be dark matter. The other possibility is that it's clumps of ordinary matter. Okay? Well, we know it's not certain types of clumps. We know it's not things like the sun because it would shine too brightly, or Jupiter or the Earth because it would have been very hard to make. So we have all sorts of arguments to tell us what it isn't. It turns out, however, that there is a class of objects that the standard model may or may not allow. We don't know. We can't calculate for sure. It's a difficult calculation that we've been unable to do, which is chunks. Imagine taking a nucleus and adding more and more nucleus, so you have a really big nucleus. Okay? That's not stable. Ordinary nuclei made up of up and down quarks, and so protons and neutrons, when they get too big, fall apart. But it may be that if instead of protons and neutrons, if you added some strange quarks to that would actually hold together, that it would be stable. And those are called nuclearites or strange quark matter, or it goes by various names. And those may be dark matter. And in fact, we're busy, many people are busy out there looking for, trying to figure out how would we look for dark matter that's like that.
You mentioned that a weak force was, if I remember the letters, mm, but you said that they weighed more than the proton? Is that correct?
There are these particles called the gauge bosons of the weak force, the W, and it comes in two varieties, plus and minus, and the Z. And they are very heavy particles that can get exchanged by other particles. So a quark can emit a W boson, one of these W particles, and then it can get absorbed by another quark. And these things are very, very massive, okay, 100 times the mass of a proton.
Oh, so it doesn't affect the proton?
Well, so the proton, a neutron, for example, can emit one of these. And this sounds very strange. How can a neutron, which weighs a unit we call 1 GeV, okay? How can a neutron emit something that weighs about 100 GeV? Okay? And the answer is that quantum mechanics tells us that you can You can violate conservation of energy. You can not conserve energy as long as you do it for a very short time. And the more you violate it, the shorter the time. So if something light can emit something heavy as long as it doesn't do it long enough to get caught at it. Okay, it has to quickly get rid of it. And it does that. So the neutron emits a W boson, turns into a proton in the process, and that W boson can't keep going away. It has to decay very, very quickly, and it does. It decays into an electron and an antineutrino. So a neutron decays into a proton, an electron, and an antineutrino, and the way we think about it is that there was an intermediate period, very, very brief, in which a W was there, but it fell apart very quickly. Thank you for joining us. You have been watching me, Dr. Glenn Starkman, discuss the Standard Model of Particle Physics, what it is, and why some physicists think it is not good enough. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, I will discuss grand unification, one of the theoretical ideas for particle physics that might lie beyond the Standard Model. Now, back to the talk. It's time to go on to talk about grand unification. Well, I told you that there were too many forces. Color, the color force, the weak force, and the electromagnetic force. And the color force holding together the quarks in the nucleus, and the electromagnetic force holding together the atom, and this weak force holding together nothing but making things fall apart. And they are described by these groups, which are mathematical structures. And we don't have to worry about the details of what they are, but they have names. The one that describes color is called SU3. And the one that describes weak interactions is called SU2. And the one that describes electromagnetic interactions is called U1, without the S. Okay? So they're just 3, 2, and 1. And you'll hear people talk about, if you wander into a theoretical physics conference, you'll hear people talking about SU3 cross SU2 cross U1. So it's just a way of describing these three forces in terms of these three numbers, these three groups. Okay. So we said that that was too many forces. And not only too many forces, we said it was a lot of particles carrying those forces. The photon, and I have this backwards, the photon carrying electromagnetism, the W and the Z carrying the weak interactions, and the gluons carrying color. Well, and there's these numbers, we said, these coupling constants that describe how strongly the gluons carry color, and how strongly the photon carries electromagnetism, and how strongly the weak bosons carry the weak interaction. Now the thing is that those numbers, alpha 1, alpha 2, and alpha 3, describing electromagnetism, the weak and the color interactions, they're not numbers. They actually depend on how you measure them. It turns out the strength of a force depends on the size or the energy of the system in which you measure it. So for example, imagine an aluminum atom. Here's an aluminum atom with an aluminum nucleus that's positively charged and all these electrons going around it. Well, the electrons that are really far out from the aluminum, they measure a slightly weaker electromagnetic force than the electrons that go around very close to the aluminum. So another way to think about it is that the electrons that are far away, they think that the aluminum nucleus has a smaller charge than the electrons that go around very close in. Okay? And this is something told to us by quantum mechanics, understood for nearly about 80 years. And it's because it has to do with how particles can come in and out of the vacuum, can materialize and disappear in empty space between the nucleus and the electrons. Okay? It's a fascinating subject worthy of a talk of its own. So, as I said, the strength of a force depends on the size and energy of the system in which you measure it. So let's look at how those do so. So the electromagnetic interaction, this alpha 1, as you go to higher and higher energy or smaller and smaller systems, it gets bigger. Okay, so 1 over alpha 1, it gets smaller. We always plot 1 over alpha 1, just to confuse people. So as we go to higher energy, it slopes downward. And the other two, they slope upward. It's just the difference between the forces, how they behave. Okay? And it's very important because when people looked at this back in the 1970s, they realized that it just so happened that they all three seemed to come together at one place. It didn't have to happen that way. They could have missed each other very easily. And that was suggestive to them because it suggested that from these many, by which I mean three, one, two, many, from these many forces, you could imagine that maybe there was just one force that they got together at this energy that they called the grand unification energy and became one force. Okay? So if we kept looking at higher energy, we'd find that there was really just one force characterized by one number, the grand unification, the gut grand unification theory coupling constant. So the idea was that we could take the three forces, color, weak, and electromagnetic, and unify them into one grand unified force. These three groups, SU3, SU2, and U1, and unify them into one group that we call the grand unified theory group. All those three different coupling constants, alpha 1, alpha 2, and alpha 3, they would become one number, the one coupling constant. And those three groups of gauge bosons, the photon, the weak gauge bosons, and the gluons, they would all be part of one kind of particle that had many different aspects, along with a couple of new particles that we call the gut bosons, or the X and Y bosons. And this is a very pretty picture that we've managed to simplify our picture down to one force, one mathematical structure, one particle that we see in different aspects, and one coupling constant. Now, it's a nice picture, but the problem was that when we went and measured how those numbers actually, those coupling constants actually run, when our measurements got better and better, we discovered they didn't quite meet. They only almost met. The other thing is that grand unified theories had a very important prediction that we could go out and measure. It had to do with protons. You see, in the standard model, protons are stable. That's a very good thing, because we're made of protons and neutrons, and if protons weren't stable, if they could fall apart, we would fall apart. Now, in grand unified theories, protons can decay. How do they do that? Well, what happens is that the quarks in the proton can emit one of these new bosons, this X boson. Now, the X boson's really, really heavy, so remember, it can't do this for very long. It has to disappear really quickly, and it does that by emitting two particles, one of which is the positron. So the antiparticle of the electron. So the grand unified theories predict that the proton can decay into a positron and some other stuff, maybe a pion, which is another type of composite particle, or a photon. Well, we can go test that. So one thing is to notice that there are lots and lots of old protons. Like we go out and we look at galaxies, we see protons. We can do even better than that, actually. So but just by the fact that galaxies exist and have existed for billions and billions of years, tells you something about how stable the proton is. We could do even better than that by taking huge vats of water with many, many protons in them and waiting and seeing if any of those protons ever decayed. And we now know that the typical proton lives more than 10 million, billion years. That's 1 with 34 zeros after it. So grand unification is an attractive idea, but so far without any experimental successes, unlike the standard model.
If you're looking for the number 1, and we're looking at all of these forces somehow unifying, could that possibly be the ancestor of everything, the singularity?
I'm not sure what exactly that would mean. Okay, so The singularity is a structure in space and time. It's a place in space and time where space and time break down. That's what we mean by a singularity. What is true, though, is that in these pictures, if you go back in the history of the universe, when the universe was much, much hotter, and the typical energies of particles were much, much larger, then at that time, according in a grand unified theory, electrons and quarks, they would be essentially the same, they would behave identically. Okay? So up quarks and down quarks and electrons and neutrinos, they would all behave identically. Photons would be the same as gluons, would be the same as W bosons. So all of the particles that we think of as very different would actually be indistinguishable in a certain in a very definite mathematical way, which would then not be, which is not true today. Okay? But we understand that there's something we call spontaneous breaking of symmetry. So sometimes symmetries of nature, like the statement that electrons are the same as up quarks or down quarks, break. So for example, if I balance this pen on my hand and I ask you which way is it going to fall, you don't know. Okay? But that doesn't mean it isn't going to fall. It can fall in any direction. So each of these directions is completely equivalent, left or right, forward or backwards. But then if I let it go, it actually does fall in some direction. It falls in different directions every time. And once it falls that way, that's a different direction than this direction. They've now distinguished things. So our picture is, in a grand unified theory, that when the universe was very hot and very young, all of these different forces were the same. All of these different particles were the same. And then as it cooled, something changed. The symmetry broke spontaneously in the same way that meaning in an arbitrary direction that I couldn't have predicted. And when it did that, the particles became different. They acquired different characteristics.
Can I ask a kindergarten question?
There's no such thing as too simple a question.
If the nucleus is a positively charged entity and the electron is negatively charged, why doesn't the electron get sucked into the nucleus?
That is a wonderful question, and one that puzzled people a lot in the 19th century. Why don't electrons? They should spiral into nuclei. As they do that, they should lose energy, and they would do that by emitting photons, particles of light, or electromagnetic waves. And the simple answer is quantum mechanics. And that's a very complicated answer, and it actually took many incredibly smart people like Newton and Bohr and Planck and Heisenberg and Schrödinger, 20, 30 years to understand exactly why that is. It is a property of nature that there is a that there is a minimum amount of angular momentum, what a skater has when they spin. There's a minimum amount of angular momentum that an electron can have when it goes around, that anything can have. Okay? It's characterized by a number called h bar, which is Planck's constant. Okay? And so an electron going around the nucleus in the lowest orbit has 1 unit of h bar, and it can't get rid of it. There's nothing it can do to get rid of it, and that's why it doesn't fall into the nucleus. If it did, we wouldn't, if quantum mechanics wasn't there, it would fall into the nucleus, and the world would look very different. But why is that? I don't know, because quantum mechanics is what governs how the world works. I'm not sure how to answer the why, except to say that is how nature is, that there's this minimum amount of angular momentum. And it completely changes how the universe looks, how the world around us looks. It's absolutely crucial for understanding pretty much the properties of every material, how nuclei work, how atoms work, how molecules work. They all depend on the fact that there is this number, h bar, that characterizes the minimum amount of angular momentum that an object can have, that any particle can have.
In your graphic that shows the three coupling constants converging at higher and higher energies, could you look at that and put those energies into more understandable form, if not in terms of common things, respectively to cosmic Big Bang age or whatever?
Absolutely. So these are in units of GeV. A GeV is the E equals mc squared energy of a proton. A proton has a mass of about an energy in mass units of about 1 GeV. Okay? So that's down here. Okay? Our largest accelerators are sitting around here at 10,000 GeV. Okay, 10 to the 4th, just below this 10 to the 5th. We're now imagining building accelerators with 10 to the 5th GeV. That's about the limit of technology. Now, the universe was, and now I'm going to have to do some mental mathematics. Let's see. The universe was, when it was, let's see, at 10 to the 10 GeV, it was 10 to the minus 26 seconds old. At 10 to the 15 GeV, it was 10 to the minus 36 seconds old. Okay.
Where do cosmic rays fit?
The highest energy cosmic rays are somewhere in about here. About, I think that's about right. About 10 to the, below 10 to the 15th GeV. They don't get up here to what we call the grand unified scale quite. Okay. So the highest energy cosmic rays are somewhere, the spot's not very bright, well, the slide's bright. It's just to the left of where they meet by about 2 or 3 orders of magnitude, by about a factor of 1,000. Yeah, 10 to the 12 or so. So we have at this moment, we have nothing that quite accesses this grand unified scale. The only way we access it is by taking a very large number of particles and seeing the very weak effects of this scale.
And what speed do these particles move at, and what speed were they moving at the Big Bang?
So particles can move at any speed except massless particles. So massless particles like photons, they always move at the speed of light, at least when they're in empty space. Okay. The other particles can move at any speed you like, depending on how much energy you give them. Okay, so an electron moving inside an atom, inside a hydrogen atom, moves at about 1% of the speed of light. Okay. You put it inside a lead atom, and the inner ones move at much closer to about half the speed of light, or a third the speed of light. So far as we know, no particles go faster than the speed of light. There was a report for a while of neutrinos going faster than the speed of light. It turned out that was due to people not quite attaching their cables tightly when they made the measurement. So far as we know, no particles known have ever traveled faster than the speed of light, nor have they in the past, according to our theory. So according to experiment, none do. According to theory, probably none have.
Could you illuminate us on what was the reason what's the origin of the concept of the Higgs boson? Why did we look for it?
Why did we look for it? That's a great question. So the Higgs boson, so let's see. So I'm just going to. So particles are wiggles in things we call fields. What's a field? We've all heard of the magnetic field. Okay. The Earth has a magnetic field. You've probably heard of an electric field as well. So you have electric and magnetic fields. The particles, light, what you experience as light, are little wiggles in the electromagnetic field. That's all they are. Little tiny oscillations in the electromagnetic field. And so if I take a charged particle like an electron and wiggle it, it causes little wiggles in the electromagnetic field that we call photons to travel from where I'm wiggling it to you. Okay. That's one kind of field, the electromagnetic field. The Standard Model tells us that there's a very important field called the Higgs field. Okay. The Higgs field is responsible, according to the Standard Model, for giving mass to fundamental particles that have mass. The electron, the muon, the tau, all of the quarks. They get their masses from interacting with the Higgs field. The Higgs boson is a little wiggle in the Higgs field. So we were really excited to we knew that if there's a Higgs field, we have to be able to wiggle it And we'll call that wiggle the Higgs boson. So if we can discover the Higgs boson, then we've discovered the Higgs field. And that's really important because it is the thing that gives mass to fundamental particles. So the truth is we wouldn't have really cared so much about just discovering another particle, the Higgs boson. What we really cared about is that discovering the Higgs boson meant that we discovered the Higgs field, which was really a linchpin of the Standard Model. The most exciting thing that could have happened at CERN with the LHC is not discovering the Higgs boson. We hope you've been enjoying the Origin Science Scholars Program. I'm Glenn Starkman, and in addition to the Institute for the Science of Origins, I also direct its Center for Education and Research in Cosmology and Astrophysics. In the second part of our talk, we learned about grand unification, the idea that the three non-gravitational forces might be unified into one force at high energies. In our final segment, I will discuss supersymmetry, another idea for physics that might be discovered at the newest generation of particle accelerators. Now, back to our talk. So we've talked about grand unification. What we haven't talked about is something called supersymmetry. So I mentioned that the Standard Model has these huge numbers, like the Planck mass, the mass that this energy, this mass that describes this weakness of gravity, divided by the Higgs mass, which is 10 to the 17th. And the claim is that not only is this number large, it is in some sense unstable. What that means is that if you very carefully arrange for it to be that large, and then you accidentally jiggle one of your many, about 19 now, maybe up to 23 or 24 parameters of the Standard Model, it'll fall down and become small again. Okay? So it means you have to sit there when you're devising the Standard Model and very carefully tune all of these 20-odd dials so that that number stays large. And the solution to that is something called supersymmetry. And here's how it goes. So remember those Standard Model particles that we had a few of? So for each one of those, what you do is you add another one. And you call them partners. So for the photon, there's something called the photino. For the W, there's a wino. For the Z boson, there's a xeno. The gluons get gluinos. The electrons are different. They're not bosons. They're what are called fermions, matter particles. So for the electron, there's a selectron. For the up quark, oh, we haven't gotten there yet, right? We have to add ones for the quarks. So there's the up squark, the down squark, the charm squark. For every single one of those particles, there's a partner, a supersymmetric partner. You notice I didn't give the Higgs a partner. It's still sitting there all by itself. I didn't forget, because it turns out you first have to split the Higgs into two different types of Higgs. There's one that is responsible for giving mass to the up quarks, and one that's responsible for giving mass to the down quarks. And then those each get partners called the Higgsinos. And supersymmetry is a symmetry in which particles and partners are exchanged. So in a supersymmetric world, just like in a grand unified world, there is kind of no difference between an electron and an up quark. In a supersymmetric world, there's no difference between an electron and a selectron, or a photon and a photino. They're the same particle, just kind of different aspects of the particle. So the symmetry is called supersymmetry, often abbreviated SUSY. Okay. Now, the instability of this Planck mass divided by this Higgs mass, we can think of as a balance scale. And if we put the Standard Model onto the balance scale, it tips the scale and unbalances it. If we put the Standard Model particles and interactions. If we put the SUSY particles and interactions on there, it would be unbalanced. But the Standard Model and SUSY particles exactly balance each other. That's the beauty of this symmetry, that it exactly balances the instability and cancels it. And so the claim of SUSY, of supersymmetry, is that the instability due to particles are balanced by instability due to their partners, so that they cancel and there's no instability. Now you might be asking, well, hold on a sec, I don't see all those other particles. And that's because supersymmetry, we know, isn't actually a symmetry of our universe right here now. But that's okay, we also knew grand unified theory wasn't a symmetry of nature. It was broken in the same way that my pen falling broke a symmetry. But supersymmetry would have to be broken at some energy just beyond our current accelerator. So the universe would be almost supersymmetric if only we could just probe that energy scale or that length scale. Now, one of the great side benefits of the supersymmetry theory is that the lightest of those partners can be stable. It's actually relatively easy to arrange that the lightest one of those many new particles that I introduced is a stable particle and has about the right interaction strength to be dark matter. And so when people go out, we've had talks in this series about people looking for WIMP dark matter, weakly interacting massive particles. What they're really looking for is SUSY, supersymmetric dark matter. So that would explain why galaxies, when they spin, don't fly apart. It's because there's all these extra supersymmetric partners to the ordinary matter. The other benefit of SUSY is that the grand unification, which failed here in the standard model because the particles the forces didn't actually meet, the coupling constants didn't actually go to the same place. You can arrange very easily that with supersymmetry, they do come to the same place. And so you get not just grand unification and not just supersymmetry, but SUSY guts, supersymmetric grand unification. And this was proposed and is one of the great successes of supersymmetry and grand unification by Savas Dimopoulos, who's a professor at Stanford and is actually my thesis advisor, Stuart Raby, who's down at Ohio State University, and Frank Wilczek, a professor at MIT, who is a Nobel Prize winner for his work on the color force. Now, as I said, you want to break supersymmetry. You want to say that it's not a good symmetry of nature. And when you break supersymmetry, it forces you to give masses to all of these partner particles. So they can't, this selectron, the partner of the electron, can't be the mass of the electron. We would have seen it if it was. It would be a charged particle with the same mass of the electron. We would have made lots of them, and we don't see them. So we have to make sure that all of these superpartners are massive enough that we wouldn't have seen them in our previous generation of accelerators. So that tells us that we need them to be heavy. Now, how heavy do we want them to be? Well, if we're trying to explain why m Planck over m Higgs, this ratio is 10 to the 17, we would like to replace this Planck by this m SUSY. So we want this number to be about 1. Remember I said we like the number 1. Okay. So if the supersymmetry scale, the masses of all these supersymmetric partners was the same as the mass of the Higgs, that would be beautiful. That would be a beautiful theory in which the symmetry breaking of supersymmetry was related to the symmetry breaking that gives the Higgs mass. And so that suggests that we should look for supersymmetric partners with masses about the mass of the Higgs, about 125 or so times the mass of the proton, 125 GeV. Well, I'm about to show you a very scary plot, and the only thing you should look at is this blue line, this blue vertical line. That's 125 GeV. And all of these green and blue horizontal lines, those are the limits on the masses of various particles in that supersymmetric universe. And when there's a green line there, that means that we didn't see something up to that mass. Okay? So we didn't see this one up to 1.7 TeV. That's 1,700 GeV instead of 125 G. And we didn't see this one up to 850 and 250. And you'll notice that all of them are way up above the supersymmetry scale that we wanted, way up above the mass of the Higgs. So what we've discovered at the Large Hadron Collider, this is a plot put out by the ATLAS detector, which is one of the detectors at the Large Hadron Collider in the big accelerator in CERN in Geneva is that there is no supersymmetry that we've seen at the Large Hadron Collider up to about 10 times the mass of the Higgs. It's also true that no supersymmetric dark matter has yet been seen in dark matter detectors. So Frank Wilczek, one of the inventors of SUSY guts, and as I mentioned, the co-winner of the Nobel Prize in Physics in 2004, said, "Supersymmetry predicts new particles with characteristic properties that will come into view as the LHC operates at higher energy and intensity. The theory will soon undergo a trial by fire. It will yield gold or go up in smoke." So the LHC is about to turn on again at higher energy and intensity, and either it will yield gold, supersymmetric gold, or supersymmetry will go up in smoke. Now, this week's speaker, that would be me, and next week's speaker, that would be Brian Lynn, we have a controversial claim. Our claim is that that big number, m Planck divided by m Higgs, that 10 to the 17, is actually 100% stable in the Standard Model alone, without any supersymmetry. So our prediction is that supersymmetry will not be discovered at the LHC, and that we will be left with the Standard Model, which is a very ugly theory, but incredibly successful experimentally. Thank you. This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins, a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream. It has been brought to you with the assistance of Case Western Reserve University's College of Arts and Sciences, Siegel Lifelong Learning Program, and MediaVision. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.